Hello everyone, welcome to OneClass. My name is Shanjida and today I'll be going over some commonly asked chemistry questions both at the high school slash university and college levels. Um, so a bit about me, I am currently a second year human biology student. And lastly, if anyone needs an additional schoolwork help or needs tutoring, you guys could check out the description box below. And other than that, we'll get started. So the first question for today says, what is the molar mass of carbon monoxide? So the chemical formula for carbon monoxide, right, which is CO. And so we're trying to find out the molar mass of carbon monoxide. So as you guys recall, that the molar mass is basically the atomic mass, but it has different units. So the molar mass is basically the ratio between the mass with the of moles of the given substance or compound. So in this case, to figure out the molar mass of this compound, what we need to do is break this down into its individual elements. In this case, we have, as you can see, we have two elements, carbon and oxygen. So, so now what we have to do is find the molar mass of each individual atom or element. So we can do this by breaking it down by finding the molar mass of carbon plus the molar mass of oxygen, right? So carbon and oxygen, as you can see, they consist of only one atom of each. So so to find the molar mass of let's for this step, to find the molar mass of carbon, we can just look at the periodic table over here and look at carbon. And so the molar mass is given on your periodic table right here, which is 12.01. So we just put 12.01 grams per mole. And then you add this with the molar mass of oxygen, and it's given here as 16.00. We have 16.00 grams per mole. Okay, so the last step of this would be to add it all up, and you get 28.01 grams per mole. Okay, so the molar mass of carbon monoxide is 28.01 grams per mole. And so this is what they have got, and this is correct. Now for question 2, what we have, it says, what is an anabolic reaction? Okay, so when we talk about any type of reactions that's going on anywhere in, for example, in our body or in any system, for example, we're talking about metabolic reactions, and there are two types of this reaction called catabolic and anabolic. Okay, so we can say metabolic reactions. Okay, this consists of catabolic and anabolic. So they're both analogous to each other. Anabolic. Okay, so where where basically your catabolic reactions is basically um, where catabolic reactions are reactions that break down large molecules into smaller molecules. Okay, so you break large molecules into smaller molecules. Okay, whereas um, your anabolic reactions are building up molecules basically. So this is where you build molecule or reaction. So for example, let's say, for example, for this, we can say that, for example, an anabolic reaction is gluconeogenesis, where pyruvate is converted to glucose, right? So, for example, neogenesis, where pyruvate is converted to pyruvate is converted glucose. And for example, of a catabolic reaction, we could say glycolysis, right? So which is the opposite. Glycolysis is where you break glucose to pyruvate. So you can see this is basically the opposite of what you're doing for gluconeogenesis. And so this is how you can compare catabolic reactions with anabolic reactions. But mainly, if we're talking about anabolic, this is where you build molecules um, or reactions. Okay? And so this is what they're saying. Anabolic reactions are building up reactions. They combine smaller molecules into larger molecules. Okay? And so the solution. Okay, so 3. So number 3 says oxygen gas has a molar mass of about 32.0 grams per mole, and hydrogen gas has a molar mass of 2.00 grams per mole. Calculate the RMS speed of an oxygen molecule when the temperature is 300 K, and 300 K means 300 Kelvin, and B, the RMS speed of a hydrogen molecule at the same temperature, so 300 Kelvin. Okay, so for A, we have to find the RMS speed of O2 at 300 Kelvin. Okay, so we have an equation here, or the room. So RMS is the room mean square speed. So it is actually the average molecular speed. So as you know that molecules are moving around in a given system, and as you increase the temperature, it starts to move fast. We're just trying to find out the speed at which it is moving at a given temperature. In this case, it's 300 Kelvin. And so there's this formula called URMS, meaning the average room mean temperature, room mean square speed. So we're going to use this equation to find out the speed, okay? Which is square root of 3RT over M. Okay, so basically your R is the ideal gas constant. So R is the ideal gas constant. And then you have P, or the ideal gas constant is, so this is a constant, so it's 8.314 joules per mole Kelvin. Okay, and so T is temperature, and this is in kelvins. And M is the molar mass. So we have M as the molar mass of the gas. So in this case, it's going to be grams per mole, right? In addition, 1 joule, so this is a conversion unit. 1 joule is equal to one kilograms meter squared over a second. Okay, so this is just a conversion unit. And for example, so for now, what we can do with keeping this in mind, we can now compute for the RMS of oxygen gas. So for oxygen gas, we just have to do RMS, so the average room mean square speed. We have 3R over M, and so we just plug in the values. So we just love 3, and our constant is 8.314. 8314, yeah, 314. 2.4 joules per mole K. So instead of putting joules, we can put kilograms meters squared over S squared, second squared, and mole gonna be times moles per K. So you have this, and then you are multiplying this by the temperature, which is 300 K. Okay. And so the molar mass of oxygen, of O2 gas, is basically, since we have 2 atoms of oxygen here, we can look back at our periodic table and see that one molar, 1 atom of oxygen is 16 grams per mole. In this case, we have 2, so you just multiply that by 2, and you get 32.0 grams per mole. Okay, so keep in mind we're using kilograms per mole in this case, so we would have to convert this unit into kilograms, right? So the conversion unit is 1 kilogram over 1 time, or it's gonna be 10,000 or 1,000 grams. Sorry, so it's going to be 1,000 over 1,000, right? So you can see we can cross out. So we can, or not crossing out yet, but we can now further simplify this. And how about I'll just write 8.3 into the power 3 kilogram. Okay, so now you can see we can cross this out, and what we're left with, and once you do the math here, you would get 483.56 10096 meters per second, right? Since your squares get cut out because of the square root, and so the URMS, or the average room mean square speed of oxygen, is 483.56 meters per second. Okay. Now for B, so okay, B, or H2, what we have, we're still gonna use the same formula. So we have U of RMS is equal to the square root of 3 RT over M. Actually, this is for the whole, this square root is actually not like this, it's the whole thing. That's what oops. So the square root, it's supposed to be over this whole. And so we're just gonna put the values that we know. And so R is 8.314 kilograms meters squared over second squared times mole 8,000. And then we have 300K since it says at the same temperature, so 300K all over the molar mass of hydrogen. So if we go back to our periodic table here, you can see that hydrogen's molar mass of one atom of hydrogen is 1.01. Times that by 2, we get 2.02. So we have 2.02 grams per mole. Right? So if you want to convert this, we just have to times this 1 kilogram over 1,000. Right? So if we compute this, we would get 1,934.244,038 meters per second. Okay. So this is the answer. Let's see. So the square root mean speeds of are 484 and 1.93 times 10 to the power of 3. Our next question says, what is the molar mass of C3H8? So this is propane. And so to calculate the molar mass, so let's say, let's write this down. Molar mass. Molar mass of propane, right? So molar mass of propane. So this is propane. So the chemical formula for this is C3H. We need to find the molar mass of C3H8, and to do that, we have to break the substance into two individual elements, right? Since we're dealing with two elements here, carbon and hydrogen. So what you want to do is first find the molar mass of 3 carbon atoms, and you add that with finding the molar mass of 8 hydrogen atoms. So if we go back to our periodic table here, we can see that carbon's molar mass is 12.01, and you just multiply that by 3. So 3 times 12.01 grams per mole. Add that with the molar mass of 8 hydrogen atoms, and in this case, one hydrogen atom has a molar mass of 1.01. So you just do 8 times 1.01 grams per mole. And so further, if we expand this, we get 36.03 grams per mole, and you add this with 8.08 grams per mole. Then lastly, you just add these two numbers and you get 44.11 grams per mole. Okay, so the molar mass of propane C3H8 is 44.11 grams per mole. Okay, so this is our next. Says, what is the structure of urea? Okay, so urea is an organic compound. Urea. So urea. Okay, so you have urea, right? The urea is an organic compound because it's made out of mostly carbons and hydrogens. Organic compound, right? Is part of a carbon molecule, or it's made out of carbons and hydrogens basically. And so the structure of urea is that it is composed of two amino groups. So and composed of two amino and carbonyl groups. Two and a carbonyl group. And so so the chemical formula for this, so let's first draw out the structure and then we can come up with the chemical formula. Okay, so let's draw this out. So since it has a carbonyl group, we know that's a double bonded oxygen with attached to it a carbon. So we have, and since it has two amino groups, so we can say that this is how it looks. Right, so these are your amino groups. Okay, so these are your amino groups. And this is your carbonyl, right? So let's come up with the formula. And so the formula for this is actually CO, right? You can see it's double bonded with oxygen. So that's your carbonyl group, and it has two amino groups, NH. Okay, so this is urea. And so this is what's given. This is correct. our next question says, how many ounces are in 500 milliliters? Okay, so we're talking about converting units basically. And so the conversion factors for milliliters to ounces is given by, so 1 milliliter. So basically 1 milliliter is equal to 0. Actually, it's equal to 0.03381 ounces. Okay, and so basically this is just the converting unit, right? You can't really derive this. It's actually a formula, or it's actually given. And so to convert 500 ml to ounces, we just have to multiply it with the conversion factor, which is 0.038814. And so what you have, so say 500 or yeah, 500 ml is equal to say 500 times 0.0338814. Okay, and so you can basically, so the answer for this is 16.907. So in this case, we're multiplying milliliters by ounces because they're the same thing. So this is how you would convert the units. Okay. So you're basically saying 500 ml is equivalent to 16.907 ounces. This is okay. So the next question here says, um, draw the Lewis structure of ammonia boron. What are the formal charges on each of the atoms? The strong intermolecular forces of attraction must be the result of the high polarity of the boron and nitrogen bond. Okay, so basically the Lewis structure of ammonia boron is given, as you can see on this page. And so the chemical formula, which should be, we should first find the chemical formula in order to draw the structure. So we can say ammonia boron, right? The chemical formula for this is CH6. Okay? And so you can see that it's comprised of 1 boron, 6 hydrogens, and 1 nitrogen. So to basically draw this out, we can say that we have a nitrogen attached to a boron, and we have 6 hydrogens, right? Okay, so we can see that nitrogen is bonding for it makes 4 bonds, where it can actually so it basically so the so basically nitrogen, since it has 5 valence electrons, it can form basically 2, or it doesn't really obey the octet rule. And so in this case, our nitrogen, right, it has 4 bonds, it would have a plus. And so boron in this case, would be negative, since if we go back to you see our periodic table here, boron is right here. It has 3 valence electrons, and so it can only form 2 bonds basically, and it's forming 3 here, so it just gained 1 extra electron, and so this is why this is negative, and therefore nitrogen is positive. And so you can say that the formal charge, so therefore you can say the formal charge of nitrogen is +1. Is +1, and the formal charge of boron is minus. Okay. So this is, and yeah, so the line that's indicated here, the line of the NB bond is a covalent bond. Okay. So this is okay. Our next question says, what is the specific heat capacity at constant volume of nitrogen gas? And so the molar mass is given as 28.0 grams per mole. And so the explanation for this would be that your specific, your specific, specific heat capacity is basically equal, or the unit for it is the ratio of molar heat capacity over your molar mass of the substance. So basically, since we are given the molar mass, so of nitrogen gas, right, which is 28.0 grams per mole. So what we just need to find is the molar heat capacity. So the molar heat capacity of a diatomic gas is basically 5R/2. So this is a formula. So you can say the molar heat capacity of a diatomic gas is 5R/2. Okay. And so, or it's 2.5R, so where R is equal to 8.314 joules per mole Kelvin. Okay, and so what we can do here is we can basically calculate the heat capacity for nitrogen gas. And to do that, we can say that, so for nitrogen gas, we can say that the specific heat capacity is equal to 5 R/2 Um, and so this is all over, or we can say, it's 2.5 R over molar mass, which is molar mass of N2, right? So 2.5 R is 8.314 joules per mole Kelvin. And so what we can say here is that and then the molar mass of a diatomic of N2 basically is given, so it's 28.0 grams per mole. Okay. And so now to figure this out, we can just compute this, and what we get is 0.742 joules. So your moles get cut out, so joules per gram Kelvin. And you can convert this, so instead of not having a decimal, you can multiply this by 1,000, and you get 742 joules. So your grams would get changed, and you get kilograms and Kelvin. Okay, so specific heat capacity for N2 is 742 joules per kilogram Kelvin. So this data, and so the solution is correct. It says, what is the mass number of oxygen? So the most common, so um, atoms or elements are found in many types of isotopes, usually three. So, but the most, in this case, if we're talking about oxygen, the most common isotope has a mass number of 15.99, which is basically 16. And this is usually given in the periodic table. So the most common isotope of oxygen, right, of oxygen has a mass number, or like the molar mass number of 16 AMU, or gram per mole. Okay? And this is given in your periodic table, which is right here. So it's a 16 right here. And so since so the mass number, or the atomic mass, molar mass, is basically the sum of the number of protons and neutrons in the atom. So since the mass number of oxygen is 16, so this means that oxygen has 8 protons and 8 neutrons. In most cases, each element will have the same number of protons and neutrons, if it's if it's a common isotope. And so this makes so your number of protons plus the number of neutrons gives you the mass number, or the molar mass. And so 8 plus 8 for oxygen would give you 16 grams per. So this is correct. This is supposed to be proton. So the next question says, what is the molar mass of magnesium? So the molar mass of this element, molar mass of, so your molar mass of magnesium, you can find this in the periodic table, or this is actually given in the periodic table. However, the way the molar mass is found basically is counting the number of protons and neutrons. However, in each usually the number of neutrons or the number of protons equals the number of neutrons. So in this case, if you're looking at magnesium, right, it has a molar mass about 24. So, and this is your atomic number, right, which is also the number of protons. So the molar mass is basically the number of protons plus the number of neutrons. And so you can see that protons, it has 12. So we have 12. And then usually it would also have the same number of neutrons, so it would be 12 as well. And so you get 24. So you get 24 grams per mole, or AMU, if you're talking about atomic mass. And so since we're talking about only one magnesium atom here, it would be this would be the molar mass of only one magnesium atom or mole. Yep. And so this is the molar mass of magnesium. Here I just rounded it, but this is whatever is given in the periodic table is the exact number. But this is how you get it basically. This solution is also correct. Question is, what is the structure of toluene? Uh, so toluene is an aromatic compound. So it is a benzene ring in which a methyl group is attached to a benzene ring. Hence, it is also called methylbenzene. Okay, so say that. So this is an aromatic ring compound. It has a methyl group attached to a benzene ring. Attached to benzene. Okay. And so since it is attached to a benzene ring and it has a methyl, so this is basically called methylbenzene, right? So with this name, or yeah, chemical name, we can also probably predict the structure of this. Since it says it's a benzene, we know that it's a hexagon, so a 6-carbon ring with the 3 double bonds. Okay. And so, and then it would be attached to a methyl, and in this case, it's attached to CH. Okay, so this is and so yes. Next question says, what is a Newman projection? Okay, so a Newman projection is a way to visualize um, the structure or conformation of a chemical bond of a compound. So it's seen from the back, from the front to the back of a compound. So basically, it's seen from the front to the back. And in this way, the front carbon is also always drawn using a dot, while the back carbon is used by um, using a circle, by drawing a circle. Okay. So Newman projection. So from this case, let's say we're looking. So there are two types of projections. We can say one's a Sawhurst projection. This is if we face it instead of looking from the side. So this is if you see the face of it. So in this case, this is how it would look like. You would have, so you would have, okay, and then this is going back, and this would be this. So and you would have dots here. Okay, so this would be, so these would be two different carbons. Okay, so this is your back carbon, and this is your front carbon. Okay, so this is a so on this is where you see your this is how you see your projection basically. Okay, if this is the eye, this is how you see it. Okay, from back. So if you're looking from the side, basically. Okay, so this is called a Sawhurst projection. So a Newman projection is the most common one, and so this is how we would draw it. So you would have, so let's see, so this is what you would have. Okay, and so you would basically draw a circle. So the dot represents the back carbon. Okay, the circle is, oh, the circle, the dot is the front carbon, and so the circle is the front, and the dot is the back. So this, I'll just this, and then you would have your projections like so. Okay, it would look like, okay, so this is your Newman projection. Newman projection. Okay, this is where um the front is red. Okay, so front is red, and the back is basically your purple. Is the circle. So back is your purple, and the black the black lines here. So the black lines here represent the carbon-carbon bond. Okay, and so this is basically a Newman versus a Sawhurst projection. Okay, this is what we have got here, and this is correct. Our next question says, um, how do you convert grams to moles and moles to grams? So this is a converting question. So basically, the number of moles of a substance can be computed by basically dividing the mass by the molar mass of the substance. since as you guys probably can recall that molar mass is basically grams per mole, right? We can use this to basically find, or so this is basically mass over n as your mole. So using this, we can basically find the number of moles if we just rearrange this equation. So you have n, right? So if I rewrite this again. So since we have molar mass is equal to mass over moles, you can rearrange this equation by basically have so moving the moles to this side, you have so you basically have m, and so since the molar mass is attached to the number of moles, you have to divide, you have to basically move this to the other side. So you have moles is equal to mass over molar mass. Okay. Since it's in the multiplication state, it would, if it goes to the other side, it would become a division. So this is how you find moles from molar mass and mass. And so now this is how we convert. So now how we convert grams to moles. And so now what we do is to find. So this would basically be grams per gram per mole, right? And in this case, what you have, basically, this is basically saying that mole over your grams get cut off, and you just have mole. And so now what you have to convert, now if you want to find mass, this is basically your formula to find mass. And so you have mass is equal to molar mass times your number of moles. So this is basically grams per mole times mole. And so as you can see, your moles would get cancelled and you're just left with grams. And so this is how you get mass from molar mass and the number of moles. Okay? And it's just rearranging the equation. And so this is how you do this question. So the solution is correct. And so that was the end of our session. If you like this Q&A, please subscribe to this channel, comment, share this video, and if anyone needs one-on-one tutoring services or has personal questions, you guys could follow the links down in the description box and ask your questions. Other than that, I'm Shanjida, and I hope to see you guys.